Hello, let's do motion. And in this video, our first one, we're going to look at just the difference between displacement and distance, and the difference in what we mean between speed and velocity. We're going to pretty much be dealing with motion in a straight line. Sometimes we'll be turning corners, but we won't be doing circular motion, and we won't be doing complicated motion as well. You might be able to hear the rain. It's raining. Fantastic. Now some terms, and you've probably heard some of these terms before, and we'll go through them in the course of these videos just to make sure everyone's using the term in terms of physics. Displacement, acceleration is a common term that you've all heard, velocity, distance. What's the difference between distance and displacement? We're going to find out in this video. Speed and velocity. Often people use them as interchangeable, but in physics they have slightly different meanings. Scalar and vector quantities. We're going to introduce you to that. You may have already been dealing with vectors in maths or heard of them, and we'll just touch on them in this topic, and we'll look at them in some more topics in a separate course of videos as well. First off, let's start with distance and displacement. To many people that would sound like being the same, however it's very different in physics. In physics, the distance is how far an object travels. That's pretty sensible, isn't it? And we refer to it as a scalar quantity in that it only has a magnitude. For example, 5 meters. 5 meters is 5 meters. Doesn't tell us which direction, but it's just 5 meters. Whereas displacement is the change in position of an object in a given direction, and that's the key thing. It's relative to its starting position, and it's referred to as a vector quantity to contrast it with a scalar quantity. A vector quantity will have magnitude, just like the scalar quantity, but it will have a direction as well. So whereas our distance was 5 meters, our displacement could be 5 meters east. Could be 5 meters west, 5 meters up, 5 meters down, but it has a direction, and that separates distance from displacement. And it's always relative to its starting position. That rain's getting quite heavy now. Fantastic. Let's do an example. Simon walked 400 meters down the road for a can of soft drink, and then returned home along the same path. So you can picture that. Walks down the road 400 meters, then comes back. What was the distance that he travelled? Well, you and I could work that out pretty straightforward. It's 800 meters, isn't it? What was his displacement at the end of his walk? Well, this is where it gets a bit tricky in terms of physics. His displacement is 0 meters because he actually returned to where he started from. So he could have gone for a much longer walk, but if he returned back to his starting position, it's still regarded as a displacement of 0 for that time period. Okay? Let's do another example. Jess cycles 4 kilometers due east and then 7 kilometers due north. Calculate her distance covered and her displacement. Now her distance is pretty straightforward. We just add it up together. So 4 kilometers plus 7 kilometers equals 11 kilometers. There's no direction, it's just 11 kilometers. Now what about her displacement? Well, we need to use vectors, or we need to basically just draw a map of what she's doing. And this would be a pretty good map. There's her starting position, and there's 4 kilometers to the east. Now notice we're representing this as an arrow, or another word is a vector, and it has an arrow on the end. And then we draw the next one. Now we're saying that up is north, and so all this is being drawn on a map, and basically we're using north, south, east, west as our bearings. And so this is the path that she walked, but the actual displacement is the distance from the start to the finish, and that's represented by this red line here. Now how would we find that length of that red arrow there? Well, hopefully you've been doing it in maths. You would use Pythagoras, and then you would have to use trigonometry to find this angle, because that red line, if we just worked it out, we have to actually try and give it a direction as well. So here's the working out. Now Pythagoras is r squared equals 4 squared plus 7 squared, and so that will be 8.06 kilometers. Now to work out the angle, so we're interested in this angle here. This is, now in this case they use tan, but because you actually know this side as well, which is 8.06 kilometers, you could use sine or cos, whichever one's your favorite one. You don't have a favorite one? Oh, you should have. Let's use tan. So for this would be the opposite, and this is the adjacent. So tan equals opposite over adjacent. That's what they've done there, and then they've done the tan inverse to convert that number into an angle, and you can do that on your calculator. Just a reminder, make sure your calculator is in degrees, and notice that in science we would give our angles as decimals. Don't convert them to degrees, minutes, seconds like you do in maths. You don't have to do that in science. Let's get rid of that writing. So the answer there was actually all that work to work out her displacement, and the answer is 8.06 kilometers at 60.3 degrees. Now that angle could be anywhere, so it's north of east. What the hell does that mean? Well, that's east, and so this is moving, we're moving it around 60.3 degrees northwards, so it's like an arrow moving it around, and that will give us the direction. Now a more common way of giving bearings would be to, let's bring it down to here, is to give it relative to north or south. That's how I was always taught how to do it. And so if we wanted to give this bearing here, let's see, that would be about there. Alright, now we know that that angle there is 60.3 degrees. What would this angle be? Let's just approximate it. It's 30 degrees. Makes it easier. Let's get rid of that 3 there. There we go. So this line here, the blue arrow, its bearing, it would be 8.06 kilometers at, what was it, 30 degrees east of north. Or it could be written as east 30 degrees north. That's a common way of writing it as well. Means exactly the same thing as this arrow here. It means exactly the same as this thing here. You just have to step back sometimes when you're giving a bearing and think, can the person who's reading this understand what I mean, and not point in some wrong direction. That's pretty much all you have to do. Right, let's do another one. Oh, let's do speed and velocity. So we've got the distance and displacement. Now what's the difference? Well, why is that important? Because the difference between displacement and distance comes into play when we define speed and velocity. Speed is the distance travelled by an object divided by time, and you've probably done that in high school. Speed equals distance travelled divided by time, sometimes written as speed equals d on t, where d is the distance, t is the time. Now what about velocity? Velocity is, however, the displacement of the object divided by time, and it looks very similar, but as we've just learnt, there's sometimes a big difference between distance and displacement. Sometimes there isn't, and you would get the same answer for speed and velocity, but sometimes there is a difference. So if we went back to Simon would actually have an average speed because we have a distance divided by the time it took him to walk to get his can of soft drink. However, his velocity would be 0 because his displacement was 0. So the speed and velocity doesn't always have to equal. And the formula we use is V equals S on T, where S is displacement. It's a bit unfortunate because D's already been taken by distance, and so we use the symbol S for displacement. And again, T is still time. and you can rearrange that fairly straightforward to solve for V, S or T simply by rearranging that formula. Now in the next video we're going to actually look at displacement time graphs. See ya!